Welcome to a short lecture on another aspect of GLHEPRO, and that is the heat pump model. It's one of the inputs. You can select one from a library or enter your own. So we're going to talk about why we need a heat pump model and what are its limited purposes. I often get questions related to certain aspects of it that go well beyond what its purpose is, so I'll explain that, and along with those come some misconceptions. We'll discuss the limitations of the model and how it's used, which is probably really the main goal. Right, so I'll talk about modeling heat pumps in GLHE Pro and how to use the model, what to do if you have more than one kind of input. But one thing I'm going to sort of skim over is how to read manufacturer's catalog data. So I'll have an example. Um, we'll look at the use of sort of what you might call the raw data as that appears in the manufacturer's table, but then they also give corrections for using, say, different types of antifreeze and different entering air conditions and so on. And I'll show you the effect of making these corrections, but I'm not going to get into the details because they're manufacturer specific. Okay, so go back to this diagram that I think you've seen before, right? The GLHE Pro, right, has at its core a simulation of the system, and one part of it is the heat pump simulation, right? And the reason for doing this is that we'd like to find out how much heat we actually extract or reject, but we'd like to start, if we can, with the building heating and cooling loads, right? And we could skip this if we'd figure out a heat rejection and extraction rate, but to do that, we pretty much have to assume a fixed heat pump COP or take some kind of iterative process. And what GLHE Pro does is it does this iteration internally. So it will figure out the heat rejected, which will change with the entering fluid temperature. So it has the advantage of this part, which I believe has to be done iteratively, I would say. Um, Maybe that's not quite right. Maybe it can be done. You can do it if you do it on like an hourly basis, calculate the temperature and the heat pump performance at the same time. But we're typically not doing that way, and we're also trying to do it fast. So, um, okay, let's go on to the next slide. So the primary purpose then is to determine the heat rejection extraction and do it in a way that's more accurate than simply assuming a fixed COP. That's the main purpose. There's a secondary purpose. We do make a rough estimate of electrical energy consumption. It's not perfect, but the heat pump model is also used for that. The heat pump model explicitly does not determine whether the design has sufficient capacity. So one question I get from people starting out with GLHE Pro is they get to the heat pump and they say, I only can choose one heat pump, but I need a whole bunch of heat pumps. Or um, I have 3 different types of heat pumps. Well, we'll get to that, but uh, specifically, the model doesn't have any concept when it runs of what the capacity is. It always really assumes that the heat pump has sufficient capacity. Okay, so other limitations. This is a very simplified model. It's really one step above assuming a fixed COP is what I would say what it amounts to. Um, the performance only depends on the heat pump entering fluid temperature, so it doesn't account for if the source side flow rate varies with time. It can account for different fixed source side flow rates by when you enter the data, you can basically enter the uh, performance information that corresponds to specific source side flow rate. It doesn't account for load side conditions changing. So uh, in a US type system with water to air heat pumps, if your zone air temperature changes significantly over the heating season or over the cooling season, right, we really can't handle the difference in performance. And if you keep the zone at, let's just pick an example. Say you have a building with a night and weekend setback. So and then you're only controlling it to 60 Fahrenheit. But when people are there, you're controlling to 72 for heating purposes. Well, that's really two different sets of load side conditions. Your entering air temperature to the heat pump will change. You don't really have a good way of accounting for that. You're going to have to make some kind of estimate in order to do that. It doesn't account for, it doesn't account for load side conditions changing. Another example, which would apply, say, in a Scandinavian or Northern European ground source heat pump system, which is a water-to-water system. So systems often operate some for heating and some for heating of domestic hot water. The set point temperatures may change considerably between the two, and the performance may change. So we don't really have a good way to sort of switch into different modes, at least not at present. It doesn't account for multi-stage operation. So if we have a two-speed heat pump, we don't have a good way of figuring out when it's in, say, the first stage and when it's in the second stage and changing the performance. It also doesn't account for cycling effects. So say in the shoulder season, you may have very low runtime fractions, and the performance may change. Also, the energy part of the calculation, where we estimate the electrical energy, it doesn't account for circulating pump energy consumption. You could, if the circulating pump's slave to the heat pump, you could actually include that in the equation fit. You could add the power consumption of the circulating pump to the heat pump. And it doesn't account for other parasitic losses. So most heat pumps have some internal electronics that are on all the time. They might only use maybe 10 watts or maybe 15 watts or 18 watts, right? And it doesn't account for that in the energy calculation. It also doesn't account for running the fan independently from the compressor. So there's a lot of things that it doesn't account for. And as I said, one way of looking at it is it's just one step above assuming a fixed COP. Okay, more limitations. GLHEPRO doesn't have an automatic way to account for the use of multiple different heat pumps. I mean, if you're using multiple heat pumps of the same type, then the way it works, it will work fine for that. But if you have significantly different performance characteristics, right, we don't really have a way to account for that in the model. So in that case, the user could create some kind of composite heat pump, right? Try to combine the performance of the different heat pumps. Or you could just try sizing the ground heat exchanger with the different heat pump models in use, and that would give you some idea of how much effect the heat pump has on the design. I'm going to say I think in many cases it will be relatively small. It's not zero, but one of the decisions in designing GLHEPRO up to this point has been related to how complex the input should be. So I've to date not felt it was really worth having the user, say, specify loads, a separate set of hourly loads on each heat pump. It could be done. Maybe it will be done in the future, but at least as through version 5, that's not the way it works. It just simply has the possibility of having loads on a heat pump with one set of curves for the heat pump and then loads directly on the ground heat exchanger. And by the way, that is an alternative. If you really feel that you have a complex situation that you need to account for, you can develop a model, say, independently, and then have GLHEPRO, or you could calculate, assuming a set of temperatures coming back from the ground, you could calculate the heat rejection rate over various time periods, and then you could specify those loads as direct. And then if you are really concerned about improving the accuracy, you could actually take an iterative approach. So you assume a set of temperature that the heat pump is seeing, and whatever the heat pump does, you calculate the heat extraction and rejection rates. With those, GLHEPRO can give you a new set of entering fluid temperatures, and you could use those. So it's possible to do a quite complex model, but it's somewhat tedious, I would say. Okay, the heat pump model itself has 4 equation fits. I think let's pause there for a second. Okay, we'll wrap this up very shortly. So the heat pump model has 4 equation fits. There is a ratio of the heat of rejection to the cooling provided, ratio of the electrical power to the cooling provided, and then for heating, we have the heat, we call it the heat of absorption or extraction from the ground divided by the heating, and the ratio of the electrical power to the heating provided. And if you notice what we're equation fitting, you see that the capacity doesn't appear by itself anywhere. We don't keep, again, we don't keep track of whether you're exceeding the heat pump capacity. We're basically assuming that you have enough capacity, or that you say have multiple heat pumps that provide this. And in GLHEPRO, we'll do a live demo a little bit later, but this is what the sort of heat pump input data look like, or not the input data, the model after you've input the data and it's computed these equation fits. And here are what I showed you in the previous slide with the ABC, DEF, and UV, XYZ coefficients. They're all here. And this is in American units, and this is in SI units. So now we'll stop here and come back with an example.